do 8.2 number 3, part A. We're going to do this in separate parts because these parts take fairly long, and they're very easy to mess up. So let's get started, right? First step in solving a linear homogeneous recurrence relation is finding the constants in the relation. So that means C1 is going to be equal to 2. And from there, we use this 2 and we put it into a function of the same degree as our linear homogeneous recurrence relation. And since our linear homogeneous recurrence relation has degree 1, as denoted by this -1 here, right, the degree of the recurrence relation is just n minus whatever this largest number k is here, right? And then you can just take the absolute value of -k to get k, right? And so in this case, k is equal to 1. So we are going to write a function of degree 1, which is just x to the 1 plus x to the 0. And the first term in the function that corresponds to the homogeneous recurrence relation always has a coefficient of degree 1, followed by this x is 0, which has coefficient of -2. And so f of x is going to be x to the 1. The reason why it's -2 and not 2 is because we are trying to, let's see, what is this, is equal to x minus 2. And the reason why is I don't really know. That's a good question. You always flip the constants to their negatives, right? So if you had 3, you would make it -3x, right? You know, if you had 4, you'd go to -4x to the cube, x cubed, right? Depending on where it is in the function. If you had -5, you'd go to 5x to the 9th, right? Just this x to the 9th depends on where in the function you are, right? So these would be for 3 totally different functions, or maybe different places inside the function, right? It's very kind of abstract, but let's try to continue along with the problem, so at least we can get this one down, right? So f of x is equal to x minus 2, and we know that this is a homogeneous function, so we can set it equal to 0. Homogeneous means equal to 0, more or less. So x is equal to 2. And now we have our root, right? We have the root of the function. We have r1 is equal to, what did we get, 2? Which is nice, because we have another equation that we're going to need to plug r1 into, and that's this function here. Sigma 1 times r1 to the n is equal to a of n, right? And the reason why this function is written out this way is kind of too hard to explain. Let's just keep going, and it'll be easier to explain later on. So let's plug in r1, right? So we can solve for a0, right? Because we know a0 is equal to, what, 3? So that's convenient, right? So we can make let n equal to 0, right? And when we let n equal to 0, a0 becomes, what does it become? 3. So we have some number sigma 1 times 2 to the 0 equal to 3, and so you have sigma 1 times 1 is equal to 3, and so sigma 1 is equal to 3. Right, and now we found sigma 1, which is nice, and we have r1, and our final answer is going to look something like sigma 1 times r1 to the n is equal to a to the n, and since we know, remember, this is going to be some sort of function, right? So we're going to be writing, we're just going to plug stuff in. What do we plug it in here? What was sigma 1 again? 3. And r1 was 2 to the n is equal to a to the n. And this is our answer. Right? And so if this was a degree 2 homogeneous recurrence relation, you would have to have sigma 1 times, since this is degree 1, you'll need one of these, right? But if there were 2, if it was degree 2, you would need 2 of them, right? And if it was degree 3, you would need 3 of them, right? Plus ... depending on how big the recurrence relation was. So that's it.